Chahraim Tovim. Good afternoon. I am Won Ho-jae from Seoul National University, a organizer on Korean side, and I have worked with Professor Ji-sun Im, who could not come, but we have tried our best to form the dream team from Korea and to maximize the exchange between two academies and have some exchanges in academically or even culturally and scientifically. And actually, it was quite impressive that working with Amnon and Moti, I found them very persistent in holding the in-person meeting. No chance of doing online meeting. And I didn't dare to even suggest them to do online meeting, because otherwise we didn't have to wait 2 years until today. Okay, so but we find that we have so live exchange of informations and ideas, and I really love this successful conference. Yeah. And lastly, I mean, really is my personally I'm very grateful, and it's my pleasure to revisit the Israel, the land of milk and honey, and we also tasted a lot of foods and fruits the land has produced, and as the scripture asks us, I'd like to really pray for the shalom of Jerusalem for years to come and for generations that follow. All right, so with that, I'd like to start the afternoon session. And I'd like to introduce, could you go back? Okay, so the first speaker is Moshe Goldstein, and he'll talk about the Photon-Instanton collider implemented by a superconducting circuit, splitting a single photon. What a challenge. That's good.
Thank you for the introduction. And first of all, I would like to thank the organizers from both countries for putting up this very nice event and for inviting me to present our work here. So you've heard the title, and maybe one way to present it is to say that if someone told you that you can take a single photon and make it collide with some fluctuation of the vacuum, and as a result split into several photons, you would think that for that you need some maybe complicated and big particle collider. But it turns out that you can do so very efficiently in a tabletop experiment, provided your table is large enough to hold the dilution fridge. So I will tell you about how you do that. This is the theory done at Tel Aviv, mainly by my student Amir Borstein, and in collaboration with experimentalists to measure that in University of Maryland, a group of Vladimir Manoucherian, and especially the work was done by Roman Kuzmin. So before I go into that particular thing, maybe just let me briefly review things that we are doing in my group, which I will not talk about, but will be happy to discuss later on with anyone interested. So we do all kinds of things related to low-dimensional quantum systems, electronic and photonic. They have a nice interplay of many interesting things. And some highlights from recently, so there are things which are more traditional solid state, like 2D materials, oxide interfaces, transition metal diagonalics, quantum Hall edges. There are things related more to cold atoms, for example, ideas about how to get interesting topological behavior, and we heard several lectures about topological systems. So how to get them instead of engineering your Hamiltonian, but actually by engineering your environment or your coupling to a bus, which also connects to the topic of non-Hermitian dissipation. There are works which are more numerical or developing tensor network algorithms for out-of-equilibrium systems. There are works on entanglement in many-body system and its interplay with symmetry and conserved charges. And there is this topic of doing fun things with superconducting circuits, and this will be the topic for today. So before we go into the system, some more broad motivation. Okay, so if we work in traditional quantum optics, then one of the basic systems is this cavity QED. So we have a two-level atom in a cavity, and therefore there is coupling between the atom and the optical modes here. And today we know how to do that in a different setup. Instead of working with optical wavelengths, we can work with microwave. Instead of a cavity, we could have this strip of aluminum. And instead of an atom, we can have an artificial atom, a qubit. In this picture, there are two of them. And the reason it's interesting to do the same physics in a different system is that while here the atom is tiny and the cavity is large, and therefore the coupling between them is relatively weak, here they are of the same order of magnitude, and therefore the coupling is very strong. And then you can contemplate about doing strong correlations physics with photons. So there are many, many suggestions. For example, this paper from 10 years ago, where you couple an array of resonators. So there are photons which can go around here, and you can implement it such that there are qubits here, which create some kind of nonlinearity, so the photons are interacting, and by playing with this element, you can induce something like a magnetic field, and this would realize for you a Bose-Hubbard model in the quantum Hall regime. So there are many fascinating ideas like that, but none of them is close to being realized. What people are able to do in the lab is much more limited. So if you look at what people are doing in the lab, this is a typical example from really the past 2 years, which is an experiment on many-body localization in an array of 11 superconducting qubits. And then you might debate to what extent this is really many-body physics. After all, 11 qubits, if you think computationally, for example, that's very easy to solve on a small computer. So the question is whether there is interesting many-body physics which can benefit from the strong correlations between photons and matter in superconducting systems, and which can be realized with current day technology, with all the progress in engineering superconducting circuits, because we want to build a full quantum computer. And okay, for me there is a natural answer, because this is where I actually started in my PhD. I was working on quantum impurities. So those are small systems with few degrees of freedom which are interacting and coupled to a large non-interacting bath. And classical examples are, for example, the spin boson model. We have a two-level system, for example, an atom which can hop between two minima of some potential and interact with a bath of, let's say, phonons. Or the Kondo effect, we have some magnetic impurities, some spin 1/2 interacting with a bath of 3 spin 1/2 electrons. So because all the interactions happen locally, this makes the system much more accessible and controllable experimentally and theoretically. But on the other hand, you can still have strong correlations, and you can have everything that you are interested in many-body physics. You can have non-Fermi liquid behavior, you can have quantum phase transitions and whatnot out of those systems. And because all the interactions occur only in a small part, then this gives you the hope that you will be able to realize that in a superconducting circuit in a sufficiently controllable way to see some interesting physics. So what kind of interesting physics, or why do that in this kind of systems? So back again to the cavity QED. If I go back to first class in quantum mechanics, if I take an atom and excite it by a photon, and it goes to an excited level, we tell our students that it will go back to the ground state emitting a single photon. And we can ask ourselves, why wouldn't it go back to the ground state emitting 3 photons or 5 photons and more? Actually, there is no symmetry forbidding that. Of course, the sum of the frequencies here should be equal to the incoming frequency. Energy has to be conserved. And nothing forbids that. The only reason we usually do not discuss that is that the coupling of light and matter, usually the fine structural constant, is a tiny number. And this is a high order virtual process. So the probability for that to happen is some high power of this small number. So therefore, it's negligible. But what would happen if we could live in a world in which the fine structural constant is of order 1? Then processes like that will be as important as the traditional single photon process. And now there is a key insight here coming from Michel Devoret of, okay, we can say, how can we live, how can we create for ourselves a world in which the fine structural constant is of order 1? So another way to think about the fine structure constant, especially if you think like an electrical engineer, is as the ratio between the impedance, the wave impedance of your environment and the quantum resistance. So for electromagnetic waves in vacuum, we have the impedance. This is the ratio between the electric and magnetic field amplitudes. And this is this number. And there is the resistance quantum, this combination of H and E. And use here 2E because everything is going to be superconducting. And the ratio between them up to this 8 is exactly the fine structure constant. And indeed, it's a small number. But then it gives us the hope that if we can engineer an environment in which the wave impedance, and although we call it impedance, it's a purely reactive thing, it's not dissipative, but if we can engineer a wave impedance of the order of the resistance quantum, then we could have fine structural constant of order 1, and then we can have interesting strong correlations effects. But how to do that? So, okay, you could say, let's play with the geometry of our environment or waveguide. But with that, we know that with a coaxial cable, the impedance is 50 ohm, and it's very hard to get just by geometry far away from that. And if we try to put actual resistor, actual dissipation, then we enter here a new degrees of freedom which can interfere with the physics we are interested in. So there is a solution, and this is what they actually did in Maryland. So instead of a waveguide or a cavity, they replace it by a waveguide, and the waveguide here consists of an array of many, many Josephson junctions. So it's centimeter long, and they have here a few tens of thousands of Josephson junctions. This is pretty impressive fabrication. So this is basically the cavity. And at the end of that cavity, they connect an artificial atom. We work in the microwave regime, and this is some kind of superconducting qubit. It's basically a Josephson junction. We see here a loop because it's a squid to make it tunable. So this is the atom, this is the cavity. Now, why is it good to build the cavity in such a complicated way? So the reason is that if we put, let's say, just a strip of aluminum, this is the usual way people do cavity in this kind of circuits, then we rely on geometry to give us inductance and capacitance, the ratio between which determines the impedance. And then when we play with the geometry, we usually modify L and C in the same way, and we cannot get to too high values. But in this setup with Josephson junctions, then the inductance is actually not geometric. It's actually the Josephson inductance. It's the kinetic energy of the Cooper pairs. And then you can have it very large, while at the same time maintaining, not changing the capacitance. And you can indeed reach inductance, reach impedance of the order of the resistance quantum. So, okay, so this is the array, and I'll come back to it. And now our atom, as I told you, is just a Josephson junction or a squid. So we have two variables to describe it, the phase difference phi, which enters in this way. This funny 2 phi is just because we work in units in which E and H bar are 1, but phi is the usual phase. And there is the conjugate variable, which is the charge, and basically it looks like that. It's like a quantum particle in a harmonic potential. Sorry, not harmonic, but periodic potential. Now, if we work in the regime, and what I will describe for you in the beginning will be in the regime where EJ is large, then it means that we basically sit near the minimum of this cosine. And to a first approximation, we just see a harmonic potential. And this is in qubit physics, people call that transmon. This is the way Google, let's say, builds a quantum computer. So we are in the transmon regime. It's almost a harmonic oscillator, this last junction. And as I told you, it's actually a squid, so we can tune its okay, this is an oscillator. It has some resonance frequency, and this resonance frequency is tuned by an external flux going through our squid. So now, okay, this is the system. We connect them together. And in the experiment, first of all, they just realized the array and put a short circuit at the end. So this is just to characterize the array itself. And they put here an antenna. They push in microwaves from here. They go here, come back, and then they measure them. And they see a series of resonances. Those are basically modes in the system, and they could see very nicely all the resonances. So basically, this is a very clean system. The modes stretch all the way from one side to the other. Okay, so this is nice. We can see all the modes, although we have here tens of thousands of junctions. And then, okay, and then you put this last element, the squid. As I told you, to a first approximation, this is a harmonic oscillator. So you couple here one harmonic oscillator to many others, and what will happen to you? So if you plot as function of the flux, which changes the frequency of this harmonic oscillator, you look at the frequency, you follow the modes. Here are the modes. So you see that you have the modes, and all the modes bend and come back. What happens to them is that there is the resonance frequency of this element, omega naught, and changes as function of flux. Whenever it crosses one of the mode frequencies, we see an anti-crossing, as we are used to in wave physics or oscillator physics. And okay, so this is just what we see here. So this is nice. This is telling us that each of the modes is actually coupled nicely to this element at the end. But this is still coupling one oscillator to many oscillators. This is not a particularly interesting physics. But then they can measure something else. So here, when we look, we see that each of the modes is very sharp. The quality factor is extremely high, something like 10 to the 4 or more. But what happens to the modes when they start becoming resonant with this last element? So it's the same plot here of the frequencies of the modes, but now there is color. So the color is the inverse of this quality factor, or you can translate it. It's basically when the quality factor reduces, it means that you send in a photon, and the photon might not come out. You lose it. And in the experiment, they excite very weakly, so at each given time, there is a single photon on the average, or less than a single photon in the system. So basically, the color here tells you that although usually this is a very high-quality system and an incoming photon gets out with very low probability of being absorbed, when you are close to resonance, suddenly this probability could become extremely high. And if you take a cut like that, you see that in this there is this resonant line shape. If you follow things along this line, so each time you change the resonant frequency and then you record the probability of losing a single photon as function of the resonant frequency as you go along the green line, so you see from different devices this, and you see that this probability reaches values of something like 1/3 in the experiment. Now, okay, so what is happening here? So clearly there is no dissipative element in the system, right? We see here that the background absorption is very low. And it cannot be that our last element is dirty or problematic or something, because usually all those mechanisms of absorption would be enhanced at higher frequency, but here we see that they are enhanced actually at lower frequency. So what we propose is that the last element is nonlinear after all. It's a Josephson junction. You send in a single photon, and due to the nonlinearity, it has a finite probability of splitting into 3 or more photons. So when you measure what comes out at the incoming frequency, you see that you lost photons. And you see that this happens at high probability of 1/3. This is some kind of spontaneous parametric down conversion, but you know, if you would do that in a BBO crystal with optical frequencies, you will need kilometer of material. Here we have a single element that does that. Okay, so how does it do that? So we need to do some theory. And okay, we have this cosine potential. This is nonlinear, but in what way? So as I said, this is large. So most of the time we sit here near the minimum. And then you can say, okay, this is not exactly a harmonic oscillator. I need to consider corrections, phi to the 4th. Another thing that I need to consider is that because this is periodic, I can have tunneling of phase or phase slip between one minimum and the other, and if the phase slips, then by the Josephson relation, I create some voltage, I create some dissipation. This maybe can split my photon. But initially, you would think that if EJ is large, then this tunneling process is exponentially small in probability, so this should be important. So we went and investigated this Kerr nonlinearity, this phi to the fourth, and you can indeed calculate, and it's easy to find the rate of splitting of a photon by that. A single photon can split into 3. But what's important is that you have those form factors, or Fs. They basically tell you, because this nonlinear process happens at the last element, so they depend on how much the eigenmode wave function has amplitude on this last element. And when you plot that amplitude as function of frequency, you'll simply see that away from resonance, there is low amplitude. It's enhanced when you are close to resonance. And this is actually a problem, because the incoming photon can couple well to the nonlinear element if it's close to resonance. But then if you split it, then out of the 3 outgoing photons, only one of them can be close to resonance and enjoy this peak. And then the others have to be at low frequency, and then their amplitudes are very, very small. So therefore, when you actually try to put the numbers in, so this is the experiment, and when you put this mechanism, it gives you a decay rate which is orders of magnitude smaller than the experiment. This cannot explain the experiment. So okay, we have indeed to consider phase slips, although we would think we shouldn't. Actually, we should. So to understand qualitatively what is happening, we can try to do something phenomenological and say, let us describe our system by a harmonic oscillator and add some term by hand which creates phase slips. And because we want a slip of the phase, we need to put here some operator which is an exponent of the charge, the conjugate variable, because this shifts the phase for you. And now, okay. And this allows you, when you expand it, to couple a single incoming photon into any odd number of photons, not to even. There is some parity symmetry, but any odd is okay. And you can calculate the rate out of that. And it has the similar structure, but there is a different form factor F. And it's plotted here in this dashed line. And you notice that in addition to the resonant frequency, it also has this peak at low frequencies. And what is the reason for that? Is that when you slip the phase in the last element, actually it cannot remain like that. All the elements must have their phases changed by 2 pi at the same time, because all the elements are coupled by strong Josephson junctions. So actually a phase slip event is a purely uniform event along the array, and therefore it has large overlap with the lowest mode, which is also almost uniform in space. And this is the reason for this peak. So now it's easy for you to split a single incoming photon which benefits from this peak into another one which is close to resonance and many photons at low frequency. And this enhancement could overcome the fact that the probability for tunneling is small because you tunnel under a barrier. So okay, this is phenomenological. There is a way to do this better, and that was studied by Jose and Glasman. We actually wanted to start from the microscopic theory and basically start from Instanton calculus and calculate the scattering. It turns out that it's possible to do so. I won't go into the details. This is the last expression. I will just comment that I was expecting to find somewhere in the literature, maybe in high energy literature, some formalism for calculating scattering cross sections for the scattering of some particle on a tunneling event of the fields known technically as an instanton, like our phase slip. I couldn't find anything, and we had to invent a formalism which we think would have other applications in other fields. But in any case, we did the calculation in our case, and this is again the experiment, and now actually there is also here the theory. This is, those colored bands are the theory, and they match nicely the experiment. And actually, this is a very hard experiment for a theoretician to work with because we don't have any fitting parameters. Basically, the result depends on the parameters of the circuit, but they measure all of them. So we don't have anything that we could add by hand. The only thing we have to help us is that they have some uncertainty in the values of the parameters that they measure. And when we plug it into our formulas, then instead of getting a line, we get this band. This is basically because of the experimental uncertainty in the parameters, but again, there are no fitting parameters. And we see that to the extent they can report to us the parameters, it is consistent with the rate that they are getting. At least in some regime, but this is detail that I won't go into now.
But can you say what is the difference between the curves? It's different.
So the difference between the curves is basically, yeah, it's different devices, it's different ratio, it's and the different devices, some of them have different impedance, Z, and some of them have different ratio of EJ to EC in the last junction.
But it's all one instanton event.
So in the theory, it's all one instanton event, yes. Well, okay, there are some other, so all those are devices with high impedance. At low impedance, we see deviations, and that might be because more than one instanton is important, although we think the reason is differently, and we are studying that, but this is something I won't go into. Okay, so this is basically the first part, and how much time do I still have left?
7 minutes, it was 30.
Okay, so there is a second part, and I won't have the time as I expected to go into even reduced details, but some points of it. And basically, okay, if we look again at our 8 on the squid, as I told you, up to now we're looking in the regime in which EJ is larger than EC, and then the phase is stuck near the minimum. From time to time it tunnels, and then we could have, and in this regime, okay, and then we could see those effects that I was telling you about. Now, then there are a different set of experiments which went to a new regime in which EJ is much smaller than EC, and when you plug in things, it also means that your resonance is so much broadened that is smeared, you don't see a resonance anymore. And okay, but it's still interesting to look at this regime, and let me tell you why. So this is the regime where Q is, the charge is almost classical because the charging energy is large, and the phase fluctuates strongly. And now, okay, so you can do measurements here, and let me present it in the following way. Actually, also there is some recent experiment by a group in Grenoble which looked into this regime, although they are not deeply here, so they saw a mixture of what I'm going to describe and the physics from the previous part. But in any case, that was also done by our colleagues in Maryland. And you can look here at the inelastic rate, and now it's not as function of the resonance frequency, but here we have fixed parameters of the squid, and this is as function of the actual frequency of the incoming photon without changing the parameters. And then you see, you can also do a theory, you can do some perturbation theory in EJ, you get this power law, and you see that, okay, if your impedance in the units of the quantum resistance, this small z, is larger than 2, then you get some inelastic rate which becomes smaller and smaller as you go to low frequency modes. But if z is smaller than 1, it behaves oppositely in the experiment. And in theory, if you look at perturbation theory, it looks like it continues, and then you can ask yourself, what is this? This looks like divergent, but how can this diverge? So the answer is that it is not. But there is another piece of physics which is coming here. And the point is that for z smaller than 1, then technically in the renormalization group sense, the Josephson term, although it's small, it's a relevant perturbation, and then it's going to modify the low energy physics. There is going to be a new energy scale, so a renormalized Josephson frequency below which the physics is going to be different. And what is going to happen there? So this is actually a well-known and old piece of physics from back from the 80s, the so-called Schmidt-Bulgakow transition. So what they told us is that at 0 frequency and temperature, basically in the DC limit, then if your z is larger than 1, then as we saw, EJ becomes less and less important as you go to low frequency. And basically, at low frequency, your phase fluctuations are so large that the junction behaves as an insulator. Whereas if your z is smaller than 1, then actually the phase gets stuck near one of the minima, because basically for the phase to move, it has to do something in the array, and it cannot. And then actually you have some renormalized reduced EJ, but below which you behave as a superconductor. The phase is localized and charge can flow. And okay, so this was assumed to be well known, but actually recently there started some debate about whether or not there is this transition. There came experimental papers questioning that and also theory. And now let me not discuss theory, but the problem in experiments with that is that usually when you do DC measurement, you apply some DC voltage and then you can create some heating, and then there is always the question of whether you're really at low enough temperature and everything. So our system is actually a good way to probe this transition because we can excite it with a single photon. So this is the minimal perturbation you can do to the system. And what I was telling you about is exactly that physics of the transition. So basically at z larger than 1, then we become more and more insulating. EJ, which is the nonlinear element, becomes less and less important, and therefore the decay rate as we go to low frequencies, it reduces. Whereas if we are at this smaller than 1 low impedance, it goes the other way around, at least at high enough frequencies. We don't need to look only at the inelastic rate. We can also look at the elastic mode shift. So there is, in addition, a phase shift of the modes. And this phase shift is basically governed by the fact that if you are becoming superconductor at low frequencies, you have a Josephson junction, which is like an inductor, which is like a short circuit or like an inductor. And if you are going insulating, then at the end of the day, you are left with a capacitor. And you can see that indeed in the two regimes, the phase shift is opposite as you would expect. Exactly from capacitor versus inductor. And this is high frequency, but we also have some low frequency measurements. And then maybe, okay, so there is still some little work to finish here. They also have some low frequency measurements, which are actually consistent with that and with this picture. And maybe the last thing I would like to tell you in theory is that I told you about perturbation theory, which doesn't work for all frequencies. It does work for all frequencies when z is larger than 1, when EJ is not important even at low frequencies. But for EJ smaller than 1, then, for z smaller than 1, then actually it's the other way around. We can simplify things if we assume that EC goes to infinity. In that case, the model is reduced to some model which is actually known to be integrable. And this makes the system pretty funny, because we have a model which in this limit is integrable, and we know that in integrable systems actually inelastic scattering does not happen. But the thing to realize is that inelastic scattering does not happen to the eigenparticles of the integrability theory, whereas we scatter photons and they have some nonlinear relation to the integrable excitation. So it turns out that actually you can use the integrability of this model to actually calculate the inelastic decay rates and understand what happens to them at low frequencies. So at high frequencies, they increase, as I told you, because z is smaller than 1, but then we reach the scale of EJ star, and then they actually start decreasing. At low frequencies, you become a linear element again. Okay, so this is the end, and you can read our current and also some papers are to come. But what I hope I conveyed you is that you can have a superconducting circuit which is so nonlinear that a single photon has a high probability of splitting, and you can use that to learn all kinds of interesting physics, both from the experiment side and from the theory side. Thank you for your attention.
Thank you, Moshe. We have enough time for further questions or comments.
Just ask you to approach a microphone.
So I apologize. I know. Do I have to press him? Oh. So I know you addressed this question, but I'm slow. Can you explain again what was the magic that allowed you to get alpha, which is over the 1? And if possible, a simple explanation.
Yes, so let me let me come back to okay, or maybe a little more back. Sorry. I think it's good to understand it from here. So we see, I mean, okay, we see that if we have a Josephson junction, it has some capacitance, and it has a Josephson energy, and the Hamiltonian looks like some n-harmonic oscillator, or in this limit it becomes a harmonic oscillator. So actually, how should I interpret that? There is some charging energy. This is capacitive energy. EC is just capacitance. And there is this term, which is canonically conjugate. It behaves like an inductance. But, okay, if you had actually just a capacitor and an inductor, the Hamiltonian would look exactly the same in terms of charge and the flux through the inductor. But if you had an inductor, what would come here would be just the coefficient here would be just 1 over L. Here, instead of 1 over L, I have EJ. So basically, if EJ is small, I mean, okay, on the one hand it's large, but on the other hand it could be small on some other scales. So then it means that you can reach large L, but not because of changing the geometry. So you have an effective inductance, which is not the one you learn about in electromagnetism from geometry of your conductor, but basically because you have kinetic energy, right? Inductance is like energy which is proportional to current square. It's like kinetic energy, and here it comes from the kinetic energy of the Cooper pairs. So you have capacitance coming from geometry, and inductance, which is not really inductance, it's coming from kinetic energy, from mass of Cooper pairs. And now you can play with both. You can change the geometry and the Josephson coupling independently, or to some extent independently, and therefore you can make the effective L over C large. In usual circuit, you have only the geometry to play with, and then when you increase L, you usually increase C by the same amount, and then the ratio between them doesn't change a lot. So this is the trick.
Okay, still more explanations. Okay, Jeon.
Yeah. So actually, the idea is you have a nonlinear superconducting Josephson junction,
yes,
which allows you to have a nonlinearity and high order terms. Then what I don't understand is even though you have a nonlinearity, the system probably you don't have an inelastic channel. So what give you this kind of inelastic channel?
If you have a nonlinear element, then if you, I mean, okay, any nonlinear element means that if you send in one photon, then it can become 3 or more photons, right? Suppose you have kernel linearity, it allows that. So usually just it's just that this effect is usually weak in most systems, definitely in optical systems. And here basically you can make it large, and this is what I was trying to explain, that you somehow live in a world in which the light matter coupling, the fine structure constant, is effectively close to 1. So also if you put an atom in a cavity and the fine structure constant was 1, then you would send in a photon, you would excite it, and it will come back and emit 3 photons or 5, because two-level system is very nonlinear element in some sense, but usually the coupling is weak. And here actually we don't have a two-level system, it's a transmon. Actually the nonlinearity in some sense is not that strong, but the coupling is very strong. So, and this makes up for that.
So for example, if you send 1 photon, then you have 3 split photons.
It can split into, actually it can split into 3, 5 and more, and you need to consider all of them because they have comparable probabilities. You need to sum over.
In that, among those kind of photons is entangled state. Can you?
In principle, yes.
I see them.
So, I mean, okay, in that sense, it's similar, right? If you send a single photon into nonlinear crystal and then it splits, then, okay, this is a way actually to create entangled photons. So in that sense, it's similar here, just that it would be pretty hard to measure that. So ideally, we would have wanted experimentalists not just to see that a photon is disappearing, but actually to see those photons that are created. The point is that they send in a single incoming photon, and it can decay into many different channels. So the probability of finding a photon in each one of them is so small that currently they cannot detect them. But in principle, if you could detect them, then you should be able to devise some experiment to show you that they are entangled.
That is very interesting. If you have two qubits, then those instants from one qubit to the other, that couples to each other, they split each other and form the entangled state, then in that case, you can detect some kind of phonon mode between these two environments, something like that?
In principle, this is possible. So we have some ideas in the future, indeed, to have a system of two impurities, and then we can see effects like the one you are suggesting.
Cool.
Okay.
So it's like when you generate spontaneously 3 or more photons, they would have special, unique squeezing properties. They're very different from photon pairs in that sense. Is that something that you considered? Because this is, in quantum optics, this is something that is highly sought for. If you have a system that can do this, that would be very interesting, at least.
Yes, I guess maybe our imagination was limited by my solid state background, and then the things we calculated are all kinds of scattering probabilities, which somehow don't look in. So basically, what I guess you suggest is to look at more complicated correlations between outgoing photons. It's related to the previous question about entanglement. Right, so to have a more fine-tuned look at them, and maybe it's possible to do so, at least in the theory. In the experiment, it would be very challenging. So I guess we should discuss.
Right, so Q.
In your last part, you mentioned that the boundary Sangjun model is, since it's integrable, you cannot explain inelastic scattering.
No, okay, so I was trying to pose a question and to answer it, and maybe I was too quick because it was the end. So I'm saying that naively you would think that integrable model is defined by the fact that the excitations are not actually only undergo elastic scattering. But the point to remember is that the excitations that go elastic scattering are not the bosons or the photons, they are something else. In the Sine-Gordon model, there are some kinds of solitons. So the solitons, they have only elastic scattering, but the relation between a soliton and a photon is nonlinear, and therefore elastic scattering of solitons translates into inelastic scattering of a photon, and you can actually use the known properties of elastic scattering of solitons to calculate the inelastic scattering of photons.
Yes, but here you are working on instantons, so that's like you are considering Sine-Gordon model in the Euclidean space. So the Minkowski Sine-Gordon equation integrability has nothing to do with your instanton case.
Yeah, okay, so so this maybe is a topic for discussion later. So actually, this was the technical problem that we had when we tried to calculate that all the calculations are done technically in all the instanton calculuses in imaginary time, and how can you get real-time things from it? And this is why we had to invent some things which that part we didn't find in the literature, because if you just try to analytically continue, the problem is that you are trying to calculate some high-order correlation function, something like a 3-point or 4-point function, and to do analytic continuation on that is a mess, and you cannot get reasonable results. So there is a trick. Somehow you can calculate directly the cross-sections and sum over them, and I think I'm going too much over time, but I'll be happy to explain later.
Maybe soliton can be elastic, but your instanton, is not necessarily inelastic. I mean, elastic. So maybe we can discuss it later.
Okay.
Okay, the last one.
Thanks for the nice talk. And then experimentally you observed that very high inelastic scattering rate, and then you developed that the theory which explained that the enhancement of the inelastic scattering rate as a dynamic involvement of instanton in your system. But do we have to see that as that we have enhanced the alpha constant. Why do we have to interpret that stuff as enhancing the alpha? I mean, of course, a high alpha is implied that we would have a higher inelastic scattering rate, definitely, but...
yeah, I mean, okay, when you actually at the end look at how the formula behaves, then you do find that the inelastic scattering is more significant at large alpha, meaning large impedance, and I was just trying to give some intuition.
Okay, I actually have a follow-up question, but due to time limit, I think we have to move on to the next talk. Let's thank Moshe for his excellent.